Alright guys, so today we're going to study section 5.3, and that's all about angle bisectors. So if you look at the notes, you will open them up and you'll see an angle that I drew you. So what I'd like you to do is pause the recording and take your protractors out, measure the angle, and then draw its angle bisector. Okay, so go ahead and do that now. Hopefully you have something that looks like this. So for the angle bisector, when I measured it, it seemed to be about a 72-degree angle, and as we know, an angle bisector is simply a ray that divides an angle into two equal halves. Okay, so I have two 36-degree angles. So the angle bisector theorem, it starts off just like our perpendicular bisector theorem said, and it says if a point is on the angle bisector of the segment. So why don't you just go ahead and pick any point on the angle bisector of that segment. I'm going to go with this one right here. And then what we have to do is we have to relate that point to our original angle. So think about that. What do you think is true about that point and our original angle? Right? Maybe you're getting to the idea that the distance from the point to the angle, to the sides of the angle, those distances are going to be the same. So I want to point out a couple things. First of all, we have to talk about the perpendicular distance, because remember, when we're talking about the distance from a point to a line, we always talk about the distance that's perpendicular to the line. The second thing is we could have picked any point. We could have picked this point down here and then drawn that perpendicular distance. And those distances would have been the same as well. Okay, so the angle bisector theorem says if a point is on the bisector of the angle, then it is equidistant to the sides of the angle. Right? Its converse is also true. If a point is equidistant from the sides of the angle, then it lies on the angle's perpendicular bisector. I'm sorry, I said perpendicular bisector. I meant angle bisector. I'm not going to start over, Matt. Okay, so why would this be useful? You know, maybe if someone was to give you, say, a project or something, and they said, hey, I need to find a point that's equidistant to these two lines, well, then you might use this angle bisector theorem. So a practical application might be if you use it to find a point equidistant to two lines. So if we turn the page, I'd like you to look at the next page, and again we have those same triangles that we had yesterday, an acute triangle, an obtuse triangle, and a right triangle. So I'd like you to take a moment, pause the tape, and I would like you to draw the three angle bisectors of the acute triangle. So go ahead, pause, and do that. Hopefully you got something that looks like this. Please notice that I did mark all of the angles, so you know what I'm talking about is make sure you're adding these marks to indicate that there is an angle bisector. Some things to notice is that the angle bisectors did all meet at a single point. So we do have a single point. If you haven't guessed already from the bottom of the page, this point's called the in-center. So using the angle bisector theorem, if the angle bisector theorem says any point that lies on an angle bisector is equidistant from the sides, what we can say is that that incenter is going to be equidistant to the three sides of the triangle. So what that means is this distance, this perpendicular distance to one side, the perpendicular distance to the other side, and the perpendicular distances to all three sides are all going to be equal to one another. So if you think of that as like the spokes on a tire, I'm going to try my best to draw a circle here, this would be the tire. It would be a circle that what we say it's inscribed inside the triangle. So the incenter, one of the facts about it is that it is the point that is equidistant to all three sides of a triangle. It is the center of the inscribed circle. Okay. Okay, at this point, why don't you go ahead and pause the tape and draw the angle bisectors for the obtuse triangle and the right triangle. Go ahead and do that.